Thank you, Karen, for the very kind introduction and also for the invitation to come here and lecture. It's really a pleasure. I have to say that I'm a bit intimidated. Judy and I have been on the island Isle since a week ago Friday, and as we travel, I'm always looking at structures. She's looking at the scenery, I'm looking at structures, and I'm making comments about the structural systems and so forth. So I was commenting on vaulting in the medieval castles and had a lot to say about the beautiful Titanic exhibition up in Belfast, but we were walking home from, walking back to the hotel from dinner last night, and the bridges along your Liffey are just incredible, and it just made me think what a history, what a culture of tremendous engineering and culture here. It made it a bit intimidating to stand here before you and talk about anything to do with structural engineering. This one, I have to say, really astounded me, because one of the things I try to do when I look at structures that I'm not that familiar with is guess what period of time they were coming from. So I knew this structure, but not well, over in the States, and obviously I knew it was cast iron. I turned to Judy and I guessed it was probably built around 1890. I was off by about 80 years. I went back to the hotel and spent most of last night researching this bridge and other cast iron bridges. To me, it's really incredible, the slenderness of it. And it must have enormously strong abutments, you know, to work on that kind of a span to depth ratio. But anyway, it's really an honor to be before you today. I'm going to talk to you tonight mostly about this structure, which we had the honor to work on. It's the 8th and final, what is called Continental Mother Temple for the Baha'i religion. It was completed at the end of 2016. It's outside Santiago, Chile. I've been practicing, as Karen said, for about 45 years. I would rank my participation on this among the top 1 or 2 or 3 structures that I've had the privilege to work on over my career. And I'll tell you why. It was an enormous challenge for a number of reasons. But I want to say at the outset that this was a tremendous collaboration among a number of engineers, and I want to make sure I give credit to everybody here over the period of several years. Engineers of various sorts, builders, fabricators, cladding system developers, and so forth. It was just a pleasure and an honor to be able to work on. Are there any Baha'i in the audience here? One. Great, okay. Well, I will take my shot at a summary of the Baha'i religion. If I mess it up, please tell me so. This is from what I've read and Baha'i that I've met along the way in the course of the project here. But the Baha'i faith is a monotheistic religion developed or originated in Persia around the 19th century. I understand that the Baha'i believe in the unity of God. That is, that one God is the creator of everything. The unity of religion, meaning that all of the gods who we may worship actually are spiritually connected to one God. And in the unity of humanity, meaning that all people are created equal, and there's a great deal of respect for diversity of backgrounds and opinions and so forth. Is that a reasonably fair summary? Okay, thank you very much. There are 5 to 8 million Baha'i in 200 countries all over the world. They have had a goal of having a mother temple on every continent, and there were 7 prior to the one that we're talking about here. Sydney, Australia, Panama City, Panama, Willamette outside Chicago, Illinois, Western Samoa, New Delhi, India, Uganda, and Germany. And here we are with this project in Santiago, Chile. You'll see some similarities. There are some design rules, if you will, and those are largely around the fact that every temple needs to have 9 elements in its dome. The number 9 is very important to the Baha'i religion. I've heard numerous inconsistent stories about why, but let's just understand that 9 is very important. And so all of the temples need to be dome-shaped at the center and have 9 elements around their circumference. This project is located outside the city of Santiago in a town called Peñalolén that is in the foothills of the Andes Mountains. And there you see, that's actually an early rendering of the project. Very challenging site. This is where the project and the story gets rather intriguing. The architect for this project, who was our client, is a firm out of Toronto called Herreri Pontorini. They've grown actually since the notoriety from this project, but they were a relatively small firm when we started working with them in 2006. And they're very academically oriented. Siamak Herreri, who is the principal designer of this, the Herreri Pontorini, is in fact a Baha'i. And there was an international design competition for this, 135 entries for this from over 80 countries. Now Siamak Herreri tells a really interesting story about the development of this. He wasn't planning to even put in a bid for the competition, but some of his fellow Baha'i and some of his friends sort of urged him to put something in. And it was almost sort of last minute that he decided to put an entry in. And one of his primary entry vehicles was that sketch that you see up in the upper right-hand side. He never expected to win. And to his great pleasure and great fear, he won the competition. Great surprise. And what worried him most was he had absolutely zero engineering input of any kind into this concept. He had no idea if this could even be built. And he was, when I met him in 2006, he was very afraid because some of the structural engineers he had worked with in Toronto told him that he was crazy, this couldn't be done, they didn't want to have any part of it, and he actually had to come down to northern US to find a crazy structural engineer who would help him with this. But no, he came to us and asked if we could help, and I will tell you what that story was. The Baha'i do not, I understand, celebrate in ordinary services like many of us may be familiar with, but gather in temples to pray together. Is that accurate also? Reasonably so? Okay. Feel free to correct me anyway, please. I certainly don't want to misrepresent anything. This is actually a fairly intimate temple. It has seating for about 500 people. Okay, its dimensions are about 33 meters across and an equal amount in height, if you will. And there you see the seating layout. This was the project team. Again, the architect, Herreri Pontorini from Toronto, ourselves, Simpson, Gumperts, and Hager. We have several offices and actually did work out of several of our offices on this, but primarily the work was done in Boston, where I work. Halpro Yales, who went through a transition and eventually was acquired by EXP over the course of this project from Toronto. They were a structural engineer at the beginning of the project who worked with Herreri Pontorini. Patricio Berthiollet is from Santiago, academic structural engineer, and his role was to ensure and convince the local authorities that while what we were doing was not strictly in line with the prescription of the code, that it was there in terms of the intent of the code. So he helped us in terms of conforming with local practice and convincing the local authorities that we were on solid ground here. Eventually, as I will describe, the project was tendered to Gartner Steel and Glass, and Joseph Gartner, a division of Gartner Steel and Glass, did a lot of the final design and engineering calculations over that. So there were 4 at various times structural engineers involved in the project. And the way this sort of unfolded was Halpro Yale started with the structural frame with the architect. We were brought in primarily to help with some of the challenges with the cladding. But the cladding, as I will show you, became so intimately involved in the structure that we wound up doing much of the structural engineering collaborating with Alpro Yales as well, trying to integrate that and bringing the structural performance where it needed to be. So that's part of the reason for so many structural engineers. As I mentioned, the superstructure contractor was Gartner out of Germany, and I'll describe their role and how they use some local labor as well. And this unusual glass, with the cladding that you see on the outside is an unusual borosilicate glass that was actually developed for this project by an entity in Toronto, which was an artistic studio, actually, Jeff Goodman's studio, with fabrication by a Toronto group called CGD Glass. Here is a schematic of the structure itself. You can see it has this spiral orientation. There are number 9, remember, space trusses that we call petals. They're in a very sort of organic motif here. And these are clad on the outside and the inside with outside with a borosilicate glass, on the inside with a thin stone, which started as alabaster and eventually became Portuguese marble over the course of the project, and I'll describe that. I'm going to back up a bit because I meant to talk a little bit about the architect's vision in this. The primary vision that Siamak Harari was going for was that this was to be a temple of light. And the light was to be the inspiration for the project. And you can see even from this model here, this is a physical model on the left, it's lit interiorly, and you can see that it has this warm, glowing feeling, if you will. This was really important to him. And that similarly, during the daytime, the sunlight would also permeate and give a warm splendor glow, if you will, on the inside. So the cladding material and the use of light, this semi-translucent material, was really important. The selection of the stone and the selection of the particular glass were critical to Siamak's vision. Siamak also wanted for the temple to have an organic quality, and the petals are meant to evoke petals of a flower or petals of a tree. And you can even see here, more so in the finished structure, but you can see part of the structure expressed there through the petals, and these are meant to evoke like veins of a leaf, if you will. So these were important aesthetic considerations in this. These were some of the design challenges that the whole team faced here. You've seen, obviously, it's a very complex structure. Each one of those 9 petals is identical, but within them there are hundreds and even thousands of individual elements. Every strut, every structural element, every piece of glass, every piece of stone within a leaf is different geometry. Very little repetition, no repetition within the leaves themselves. The architect wanted very high precision in the fit-out. The joints between the glass and stone elements had to be quite narrow, and they had to be of a consistent dimension. The materials had to appear to be, and in fact need to be, a very high quality material. One of the big design challenges from a structural point of view is that the project site is in an area of very high seismic demand. If you're familiar with seismicity at all, the zero period acceleration, which has a 10% and 50-year chance of occurrence, is 0.41 G. We sort of relate that in the United States to California levels of seismicity. So this is a very high seismic zone. The alabaster that the architect had chosen really had no track record in a thin cladding application. It had rather variable strength. It had some veining in it, beautiful, but the veining produced variable structural properties. There are no industry standard specifications for designing in alabaster as you might find for granite or marble or more traditional thin stone applications. To compound all of that, the structural properties of alabaster can degrade under high temperature or under high levels of moisture, and particularly under prolonged combinations of high level of moisture and temperature. So not an ideal material, but the architect was absolutely in love with the material. The glass I will describe to you again was a new material developed for this project. Again, no industry standard or guide specifications for its use. On top of all of that, the owner said they wanted a 400-year design life for the structure. We told them we weren't going to promise them a 400-year design life, but the best that we could do was to use all the tools at our exposure to tend on the longer design life side of things than might be typical, a typical 50, 100-year design, at least in the United States. So we have a lot going on here. I went to school actually on the West Coast to learn seismic engineering, which is probably why I got drawn into this project, even though I work and live on the East Coast today. And this project is attempting to do everything my professors in college told us not to do. Heavy, brittle materials in a high seismic zone are known to be a no-no. So how do we make this work, help the architect meet his design vision, and really do it in a responsibly safe and reliable way? That was the major challenge for structural engineering on this. A little bit more on the skin and cladding. The outer glass is 32 millimeters thick. It's made of borosilicate glass, which is Pyrex. This is the stuff that we make beakers and test tubes out of. Pyrex is actually extremely strong in its purest form, stronger than ordinary soda lime float glass, but it's expensive. But to get the texture and the appearance that the architect was looking for, this glass was made by taking nodules of Pyrex. Think of a piece of Pyrex, maybe the size of your finger or your thumb, broken up and put in a mold in an oven and heated up and then fused together, melted and fused together, but fused in a way that you could see the fusion lines, and this was the texture that the architect was going for. I've described the alabaster. That also is to be 32 millimeters thick. The panel sizes vary, but the largest are around 1.5 meters on one side, mostly triangular and trapezoidal shapes. I talked about the alabaster and its qualities and its challenges, if you will. And mostly we were very concerned about degradation over high temperatures and high levels of humidity and what we could do about that. But to get the texture and the appearance that the architect was looking for, this glass was made by taking nodules of Pyrex. Think of a piece of Pyrex, maybe the size of your finger or your thumb, broken up and put in a mold in an oven and heated up and then fused together, melted and fused together, but fused in a way that you could see the fusion lines, and this was the texture that the architect was going for. I've described the alabaster. That also is to be 32 millimeters thick. The panel sizes vary, but the largest are around 1.5 meters on one side, mostly triangular and trapezoidal shapes. I talked about the alabaster and its qualities and its challenges, if you will. And mostly we were very concerned about degradation over high temperatures and high levels of humidity and what we could do about that. One of the reasons that we were awarded this structure is that our firm, Simpson, Gumpertz & Hager, has some unusual, I would say, for a structural engineering firm, capabilities, one of which is that we have a very extensive structural and material test lab. And so we were able to bring these new or unusual materials, the alabaster and the glass, into our laboratory, apply a lot of torture testing that we invented for that purpose, and to understand the structural properties and durability of these materials. So you see here, for example, some testing of the alabaster. We're doing here a 4-point flexural test in our laboratory to understand the flexural strength. And we actually tested samples that had been degraded to various levels of temperature and humidity and duration to understand the behavior and the deterioration of of the material. You see in the lower right-hand side, and I know you can't read the numbers there, but this is basically looking at the variation in strength with temperature and duration of temperature. And what we found generally was that the structural properties of the alabaster would start to degrade around 40 degrees C and would go down pretty linearly with temperature. On the left-hand side is actually an analysis that we made of the actual daily yearly regimen of temperature that the alabaster would be exposed to. And we were able to use that and calibrate to the testing that we were done to understand how badly the alabaster might degrade over its life. And so when we did structural testing, we actually we used design properties that were corresponded to the ultimate degraded state over the life of the structure, if you will. What we learned from all of this was that it was technically possible to make the alabaster work and work in a way that was safe and in manners that were consistent with general levels of structural reliability. But it meant that you had to keep the interior temperature of the alabaster reliably within certain limits. In other words, and the way that that was handled was that the plenum between the outer skin and the inner skin was actually the plenum where cool air was circulated. And it meant, in effect, in some measure, it's a slight exaggeration to say, they had to keep the air conditioning on all the time in order for the stone not to degrade. And that was proven to be impractical. I'll return to that in a moment. Here is the borosilicate glass. You can see the elements broken elements going into the oven, and you can get a sense for the texture in the lower right fixture, which is exactly what the architect was going for. What we were most concerned about with the borosilicate glass was not its inherent strength or the reliability of the basic material, but how good and durable and strong the fusion lines would be between the various nodules. So we used some industry standard tests and made up some more that were even more severe to see through freeze-thaw or thermal shocking if we could degrade those bond lines. And the bottom line is that the material was extremely tough. We couldn't damage it at all, short of really dropping off the top of the Empire State Building or something. It turned out to be very strong. What you're looking at here in the upper section is a cross-section of a piece of glass, and that blue that you see is dye penetrant, the kind of dye penetrant you would use for weld inspection to see if there was any degradation in the bond lines, any separation after our torture testing, and it turned out that there was not. So the glass turned out to be extremely strong and quite durable. So now to the structure. Here's the structure. Because we're in a high seismic region, the only way we could really make this structure work was to apply base isolation. The base isolation was used I'm seeing some nodding heads here. We used friction pendulum isolators in the horizontal direction. We didn't isolate for vertical. This now was about 10 years ago, so vertical isolation was not as prominent as it is today. But we achieved very good isolation in the horizontal direction. So it turns out that actually the vertical accelerations, and there were significant vertical accelerations because we're fairly near source here, they wound up dominating the design. And the interesting part of the structural behavior when we did the dynamic analysis is because of the spiral geometry, when you accelerate the structure up and down, you actually get this twisting effect. Did you ever have Jiffy Pop popcorn over here? No. This is a U.S. thing. All right, sorry. It won't mean anything to you. I won't even go there. It's too long an explanation. I can do it over Q&A if you want to. We said it behaved like a Jiffy Pop popcorn popper as it went up and down and spiraled, if you will. So we got not only vertical accelerations, but lateral from the vertical acceleration. So the structure is built on a concrete podium. And you'll see some of that in construction later. And just at the level of the base isolators there is the top, think of a round open top table with base isolators on it. And then those structural leaves are sitting on top of the base isolators. And the structure itself is a steel space truss, the geometry of which was largely, it was a bit of an arm wrestle between the architect who was looking for this organic kind of geometry and the structural engineers who were looking, as we always do, to try to optimize the structure. So there was a lot of back and forth between us and the architect, we structural engineers and the architect, over the geometry. Because we had really no design standards for the alabaster or the stone, we couldn't go back to sort of classic prescriptive design where we're working with characteristic strengths and factors of safety. And we have all of these pieces of stone and glass overhead. We were very concerned about falling potential. And so we went back to first principles of performance-based design, which I think is more common in the US for seismic design now than it is in other parts of the world. But in the US, performance-based seismic design was really developing as we were going through this, and we had people who were involved in that development of that approach to engineering. Basically, in performance-based design, you're choosing target levels of performance and target levels of reliability, if you will. So you're looking at the variability of load and resistance and the probability of failure being where those two overlap, if you will. So we took all of our laboratory testing to understand the variability in load, the resistance. We have a lot of data from industry about the variability of the seismic loads, for example. And we adopted, based on then developing measures, criteria for performance-based seismic design, a criterion that that there should be no more than a 10% probability of failure of any single panel, that any single panel would drop under an earthquake with a 10% probability under the design level event. That was our goal. Anything more than that would be unacceptable in terms of risk to life. And we went through a lot of analysis, and this was a tremendous amount of number crunching where we actually calculated the probability of failure under the seismic events of every piece of stone and glass and element in the structure, thousands and thousands. So we're writing script and crunching gigabytes and gigabytes of data to do this calculation. And this just shows a piece of the spreadsheet that shows the output. The really interesting and satisfying thing as we did all of the calculations was something really interesting came out of this as a design tool. The original calculations that we had for stone and glass failure turned to be out to be over our limit of reliability. That is, we weren't beating our target. But we were able to go into the structure because we had the probability of failure calculated for every piece of glass and stone. We could see what parts of the structure were contributing overly to the probability of failure, and saying we've got a problem with that part of the structure, we need to take care of it. So most of this involved looking at parts of the structure that were vibrating or accelerating too much, going back to the architect and saying we need to make some changes to stiffen up the leaf in that area and this area in order to bring the accelerations into line. Because there was a really small percentage of elements that were leading disproportionately to the probability of failure. So it was a really interesting design tool from that perspective. Once we did all of that, our sort of back check was to go back and see, well, what are the inherent safety factors that we're dealing with here in the most highly stressed structures? And they came, most of the stone and glass elements were in the range of 3 to 6, which is actually pretty reasonable for most masonry elements, if you will. So we took some measure of satisfaction from that. But in the end, we needed to move away from the alabaster. And there were really several reasons for that. The one and dominant one was that having the air conditioning on all of the time was just not sustainable or reasonable. We were looking at, backup systems, what would happen if the air conditioning went down for 48 hours and things like that. As we're going through this project, and remember we started in 2006 with the engineering, but the imperative for sustainability was growing. It was becoming very important to the owner, and eventually, it became impractical. The other problems with the alabaster were that Santiago actually has a relatively aggressive environment. There's a lot of smoke, air pollution there, which we thought would require a lot of cleaning for the alabaster. To do that with a stone that's relatively soluble is not very practical. And also there was a limited quarry capacity for this particular stone. So with all of these piling up between the structural engineer beating up on the architect on one side and the owner beating up on the other because of the sustainability problems, the architect had to surrender his desire for the alabaster. And we were able to find a Portuguese marble that actually was very close in appearance. It didn't have all of the problems. So we did another series of testing, reran the reliability calculations for the Portuguese marble, and made that change. Just a little more on the design of the structure. This just shows some of the, again, seismicity was dominating here. We did hundreds and hundreds of seismic analyses using the response spectrum method to calculate the in-plane and out-plane accelerations of every piece of stone and glass there. And you just see some color contour plots from some of that analysis. We were able to bring in here, we've done this type of work on different type of structures. We have a group that in our engineering mechanics division at SGH that does a lot of work on structures like this. These are very precision, generally scientific and defense radio telescopes and radar antennas. And although the structure doesn't look a lot like the Baha'i structure, I think you can appreciate the analytical techniques would be very similar and translate over. So we brought those folks in to help us with this. We also had to do a lot of work with tolerances and movements between different panels because we had very tight joints. There are no expansion joints anywhere in the facade, and so we had to have facilities to take up all of the structural movements between each piece of stone and each piece of glass. And we calculated the gap changes during all of the structural movements as well. In this we used some of this is not Bahai Temple, this is another structure that we designed the Epcot Center and Walt Disney World, the geodesic dome that you see there. Much more regular panel system, but we borrowed some of the concepts that we had for drift and tolerances between panels from that project. So just to go into a little bit more detail on details here, the basic geometry of the panels for the stone and glass matched the geometry of the underlying structure. We had a structural frame, and then we had subframes that had components for glass and stone that mounted either on the outside or on the inside of the structural frame. This again is just the analyses for drift tolerances there. And then we had to figure out how to mount these panels so that they could move and they weren't overly constrained. And there's a lot of detail here that I won't have the opportunity to really go into, but we use different techniques in order to try to support the panels in a statically determinate fashion, but still allow them to be stable. And so we had, I think you can see, let me see if I can get the pointer going here. Yes. This is an alignment tab that comes out from the base of the structure, and we have these adjustable screw stops on each side that could limit the movement of the joint from side to side. So you're dealing with adjusting the permissible movement and the position of the gap between panels by adjusting these screws. And then in terms of fixity along the direction of one of the frames, we had a similar kind of arrangement with screw adjusters that would back up against a stop here. So we were able to align in the field the position, and there were different alignment techniques depending on where you were on the structure and how the gravity load and other loads were being carried. We're going into some of the design. Here are the design of the glass panels here. This just shows you the glass with an aluminum subframe, and these are some of those lateral screw stops that allow for the joint alignment. This is one of the stops that these go against. Here you see the underside. All of the glass panels and the stone panels were fabricated in Europe and sent over. More details here showing some of the waterproofing details. All of the joints waterproofing joints had backup associated with them. This one detail here, and I don't think you can really understand all the details from the back of the room here, but we spent more time on this one detail than any detail in the project. Literally hundreds and hundreds of hours went into this, because what we're showing here is the relationship and the attachment of the basic structural frame, which is this tubular element down here, attaching the glass on the outside. So here we have the demands of the structural capacity, adjustment for tolerances, and keeping a weather enclosure there at the same time. On top of all of that, the architect would not permit the appearance of a fastener on the outside. So we had to come up with some kind of blind fastening system. So we have all of these conflicting demands, and how do you solve that? I will say one thing that we decided on early is, in terms of sequencing, that the stone panels would go on from the inside first, and they could be back fastened by application from the outside. But then the real challenge was putting the glass panels on in a way where no fasteners would be able to be appeared. At the same time, having waterproof joints between the panels and being able to adjust for all of these tolerances. So some of the elements here that you see, you start with the structural frame. This element here, this U-shaped element, is a rubber-shaped gutter, which is a water management channel, if you will, that will take backup water in the event that the primary seal between the panel fails here. That water can be collected in this gutter, and there's a network of joinery in these gutters that take the water on the outside. Here you see the glass that is attached with undercut anchors to this aluminum extrusion, one on this panel, one on that panel. And this bar right here that you see is actually a toggle bar that clamps the subframes down to the frame. And so the way that you assemble this is a bar that's about an inch wide and about 6 inches long. And it is arranged in a toggle so that during erection, it's aligned with the axis of this member. The panels can be dropped over it, and then from the outside, working through this joint, the toggle can be turned, and using a tool from the outside, you can clamp it down in position. So it's all blind fastening done from the outside. And you need to clamp it a certain amount so that you compress this gasket system, but not over-compress it. Anyway, that's the short version of the explanation of how this complicated joint. More engineering went into this than any part of the project, but it works. So I'm going to go to some construction here. We're looking at the same sort of detail. This black here is the U-shaped neoprene gutter system. These are the toggle bars that I just mentioned. Probably a lot easier to understand from the. So you see they're aligned along the axis, ready to accept panels. Now it comes to who's going to build this thing. This is really a challenge because very, very high precision structure in an area where generally the degree of sophistication in the construction labor is not that high. An owner who wants a very high degree of reliability and so forth. And there was an imperative actually on the owner's side in order to be able to use local labor in the construction here, even though we recognized they couldn't do all of it. So we went on a search for the owner and determined that there were probably 3 or 4 contractors in the world that we really felt with a high degree of reliability could put this project together. And I won't mention who the other ones are, but after a lot of interviewing, we settled on Gartner in Germany. You may know them. They're a subsidiary of Permis de Lisa. They've done a lot of really fancy cladding work, if you will, and a really excellent engineering and quality control team there. And after a lot of negotiation, Permis de Lisa was selected for the project. We did also agree that the delivery system would be basically design-build. That is, we would tender the design over to them, but they had to do the final design calculations and take complete integrated responsibility for the design and construction of the structure. And that worked very well. Here we're doing a mock-up, a visual mock-up at Gartner's plant in Germany. This is the largest water testing facility I've ever seen. What you're seeing here is a very large mock-up of the panel system at Gartner's plant in Germany, and this grillage is a bunch of spray racks that we used for testing. And we actually breached or cut the primary seal in the water testing to make sure that the backup seal was reliable enough to do the job. Every component of the structure was digitally fabbed. These are, you're seeing plasma cut steel nodes for the joints. Every piece of aluminum frame and stone and glass was digitally fabricated here. Here you're seeing a lot of the glass elements with the undercut anchors on them ready to go on the frame, and glass frames becoming assembled. Construction on the site started around 2012. It was completed in 2016. The structure itself actually went up pretty fast, but now you're seeing site work here of the foundation and steel going up, rebar for the podium. There was a central tower that they erected to start the structural steel erection. You see the steel going up here. This is a good shot really showing the complexity of the structural steel. A lot of the space truss elements now in place, the rubber gasketing going on top, and we're getting ready to accept panels. Some of the marble panels going up on the inside first. There's a view from the podium level. And we're starting to erect glass panels for the final enclosure on the outside here. Really complex geometry. You can see the variation in all of these sizes. One of the design objectives the architect had was that he wanted a worshiper inside the temple to be able to stand at the middle and look up through the oculus and have the impression that you were looking through a canopy of leaves in a tree up towards the heaven. And he was very thrilled with the result. That is the oculus of the sphere, of the temple. This is a view near completion down at the worship level, which is at the podium. Some of the details around the podium. It's really a fantastically beautiful structure. There it is complete with the, you can just see the city of Santiago down below here. There's some stunning views. There's a reflecting pool there. So these are some of the challenges that we faced. These really novel materials in a high seismic zone that we solved using performance-based design, a lot of digital design and fabrication. There are 2,500 panels on each of those pedals, and each one is unique. A lot of really heavy data analysis. We couldn't have done this project 20 years ago. There just was not the computational horsepower or the digital fabrication to do what we were able to do here. The owner, both the architect and the owner were really, really pleased with the result. And this temple actually has become a destination point for the city of Santiago. They have averaged in the first couple of years now 30,000 visitors each week to the temple. So people are actually going to Santiago to come and see not only Bahai but others. So it's been really, really a tremendous success. Just some eye candy shots here in various atmosphere. Beautiful, beautiful structure. There you are looking down over Santiago. That's not a model, that's the real thing. So you see here a rendering from the original design competition on the upper left and on the lower right, the finished structure. So let me pause there for questions, and I would just like to spend 5 minutes or so talking about some of the things that the U.S. Structural Engineering Institute and IStructE are doing together. But let's finish with Bahai. Do we have time for questions, Karen? Okay. What questions might you have? Yes, sir.
Has the structure experienced any large seismic events?
Not large, very minor events, nothing that you would even worry about. Yeah, we have accelerometers actually on site. There have been some small earthquakes, but nothing that would bother it yet. Yes?
Just you were talking about tolerances, and as you clad the building,
Yes.
and the shape deflected, did you have to monitor that on its way up? Was it a constant ongoing process?
Yeah, we actually worked with Gardner and did a stage-by-stage analysis of the deformation of the structure. It's actually a pretty stiff structure, so that there wasn't too much of a problem there. But we did make allowances for future movements in the joints and the alignment. We also did a very complex probabilistic analysis of tolerances that proved that this thing could actually go together within the tolerances that we prescribed, using presumptions of variations in various dimensions and so forth. So that helped to make people comfortable as well. Good question. Yes.
Thank you very much for the presentation. Very interesting.
Thank you.
The architect request that you mentioned in the beginning, 400-year design life. What's the realistic figure you were able to give back?
We didn't give them a number, but I would say 100 years is a reasonable expectation. You know, if you pushed me, I would say it's a good 100-year structure, maybe more. And that came from the owner, by the way, not the architect. The architect understood it was unrealistic as well, and he didn't want to accept, the responsibility for that either. But definitely, I think the levels of performance are above the standard structures that we would design in the United States. So, yes, I think we achieved a good, reliable 100-year design life. Yes?
And with that 100-year design life, is there maintenance required for the structure? Or any change, like if you need to replace any, which we expect them to be, if you need to replace anything, if anything gets damaged or if you
Yes.
on it? Has that been
Primary maintenance is cleaning. We thought a lot about maintenance. Cleaning. The glass should be pretty durable. The stone should be pretty durable. So that's going to be okay. The sealant joints will need to be replaced probably every 20 years or so, something like that. That's probably the biggest maintenance thing. Fortunately, you can get everywhere on the structure from the inside and the outside with hydraulic lifts, so that's all possible. So those are the major things. We we have a lot of attic stock for the cast glass and the Portuguese marble in the event that a panel would be broken. They would still have to be fabricated to the right shape. We couldn't obviously buy an extra piece for every the hundreds of pieces that are there, but we have enough attic stock to last some time in the event a panel is damaged or something else happens to it. Yes, good question. Any others? Yes.
You mentioned that you put some accelerometers on the structure. Do you plan on reassessing
Oh,
the
they're-
reliability in a few years when you have the actual loads on the structure?
The accelerometers are base motions. They're not, we weren't able to convince them to put accelerometers on the structure itself. I wish we had, but there were budget constraints and we weren't able to do that. So it's not a fully instrumented structure. But we can track how the isolators are doing and what the inputs are for that. Yes, great question. There's one up here.
No, it's the same question.
Same question, okay.
Just in terms of digital fabrication,
Yes.
so the fabricator has got his own digital model, or he take it from the structural engineer?
Yes, we handed our models over to the fabricator with warnings and so forth, for appropriate protections, but we handled our models over. They used them for the basic geometry, and they worked with them. I think they used SolidWorks ultimately. We were working in CATIA models and we had a bunch of different models going, but they did their fabrication off of SolidWorks eventually. Yeah, good question. Okay. If you have 5 more minutes, I would love to tell you about some of the things that SEI and IStructE are doing together. Because to me it's very exciting, and I've had a foot on the boards of both institutions for a while, so we've been working together to see how we can improve the practice of structural engineering to make the world a better place, if you will. It's a lofty goal. For those of you who don't know, SEI, the Structural Engineering Institute of the United States, is an institute of the American Society of Civil Engineers. So we're organized a bit differently than the UK system in that there's a separate ICE and IStructE generally here. Here in the US, the structures are considered to be a subdiscipline of civils, and so we have the mother organization, the American Society of Civil Engineers, and then the Structural Engineering Institute is below that. We have about 30,000 members in SEI, very similar to IStructE, but whereas IStructE has about half of their membership outside the UK, we have about 22% of our membership outside the UK, and frankly a fair fraction of that, or outside the US, a fair fraction of that, that 22% is in Canada and Mexico as well. So we're very much North America centric. Having said that, we're similar in a lot of ways, we're different in a lot of ways, but I think we have different strengths and weaknesses. The institution, as you know, is very strong on professional credentialing. IStructE is the globe standard, global gold standard around the globe. SEI is very well known for creating design codes and standards, like ASCE 7, if you're familiar with that. So we have a long-standing relationship between the two organizations, but we have determined really 5 or 6 years ago to do much more together, to try to work together to advance the practice of structural engineering and not compete with each other for territory, but rather to help each other. So we started having biannual leadership meetings. Joe Kindergan and Martin Powell and others were over in the US in April to meet with our leadership. We get together and we talk about how we can work together. Where is the profession going, and how can we work on things together to improve the profession? So we're working on questions like, can we actually offer joint licensing or credentialing? That's a difficult issue because in the States our licensing is very complicated by the fact that we answer to 50 states. You can't prescribe structural credentialing at the federal level. It's the purview of our individual states. But we looked at, for example, offering a joint student membership across both institutions. So if you're a member of one, you're the member of another, of the other, which would be great. We've had joint membership on various professional committees. We have a strong committee going now in the U.S. on advancing performance-based design in other areas than seismic. And we have an institution member sitting on that, and we do the reciprocal of that as well. There's a lot going on with younger member collaboration and joint conference. A few of the particular exciting things that we have going on now is just 2 years ago, the institution developed a comparability exam with the U.S., which says that if you are a U.S. licensed structural engineer, you can sit for this comparability exam and interview and earn IStructE. So we have a path in one direction. We're trying to work on the other direction, but it's again complicated by the state system, but we're working on that. And we've had 2 sittings so far. Our annual SEI annual conference is called Structures Congress, and in 2018 and 2019, the institution sent an examining team over to Structures Congress to examine structural engineers who wanted to obtain IStructE. That's really exciting to me. I assume you're familiar with the CROSS system, which was developed by Alistair Sohn in the UK. Alistair has this vision to take CROSS international. So we have a CROSS South Africa, we have a CROSS Australia. This year, we're developing a CROSS US site. So that should go live actually in another site. You see here a screenshot from the developing. Look for it. It'll be cross-us.org. And there'll be announcements going out in about a month's time on this. We also decided that we wanted to do joint international conferences together. And we'll be holding our first international conference in Dubai on 29th and 30th of September in this year. And the theme is called Iconic Global Structures, What Can We Learn? And it's going to be, I think, very exciting. The approach here is that we've chosen a number of structures from around the world and have worked on various themes. Like there's one session, for example, on tall buildings and performance-based design. And we have one from the east, we have one from the west, we have one from the Middle East, example project, structural engineer, keynote speaker, and other panelists. And we talk about each of those projects and compare and contrast how they unfolded in different parts of the world. And the theme, the objective there is to learn how geography plays into the way that things are done around the world and what we can learn from each other. So that's going to be really exciting as well. So there's a lot going on with that. Your current president, Joe, has been to the U.S. If he hasn't talked to you about that yet, he made a trip back in April. You'll probably hear from him pretty soon. So we're having a good time collaborating together. There's a lot that we can do together, and I'm very excited about where that can take us. So thank you very much.